Today on Macaulay Math, we're talking antidifferentiation and the definite integral. Intro. Okay, good day. I'm Professor Macaulay. This is Math 200, Calculus 1, Lesson 21 on antidifferentiation and the indefinite integral. Our goals for today. We're going to write the general solution of an indefinite integral. We're going to use indefinite integral notation for antiderivatives. We're going to use basic integration rules to find antiderivatives, and we're going to find the particular solution of a differential equation. This lesson introduces the final major concept for this course, antidifferentiation and the indefinite integral. While the integral has a number of significant practical applications, the process for finding the integral at its core is little more than the reverse of the differentiation process. The antiderivative and the integration process. A function capital F is an antiderivative of lowercase f on the interval I if the first derivative of capital F of x is equal to lowercase f of x for all x and I. Some notation for antiderivatives in the context of this first definition. The differential form that we talked about at the end of the last unit is dy equals f of x dx. The integral notation of that will be that y is equal to the integral of f of x dx, which will be equal to capital F of x plus some constant c. This symbol right here is known as the integral symbol. The general solution versus a particular solution. Since the derivative of a constant is 0 and the antiderivative is an indeterminate form called the indefinite integral. Let's define some of the notation here in this diagram here. So we have y equals, the variable of integration is this dx. The integrand is the function that is going to be integrated. The result is called the antiderivative, and this constant c is called the constant of integration. This constant c is why they call it an indefinite integral, because we do not know the value of that constant that we would lose when we do the derivative. An example, the derivative with respect to x of y equals x squared plus 4. Recall, the derivative of a constant is 0. So the derivative of this thing, we bring down the 2 and reduce it by 1, and so our derivative is 2x. But if I didn't know this to begin with, when I go to do the integral of 2x, I should get the original result. I have the x squared plus some constant c. If I didn't know what the original constant was, this c represents a placeholder. As it is written here, x squared plus c, this is called a general solution. This is very important. Note, we must add a constant to hold the place of the constant from the original equation. Again, this is very important. If you don't put your plus c when you do an indefinite integral, you will lose points. Some simple integration rules. The integral of 0 is a constant. We don't know what that constant is, but it is a constant. The integral of a constant, here my constant is k and my variable of integration is x, so the result of this integral is kx plus c. Some more simple integration rules. The constant multiple rule. If you are trying to integrate a function that is multiplied by a constant, you can move the constant out in front and then do that integral. The simple power rule for integration is just the opposite of the simple power rule for differentiation. In the case of integration, you add 1 to the exponent and you divide that result by that variable plus 1. And again, we add the c. The sum and difference rules. If you take the integral of a sum or difference of two functions, then you can separate that into the integral of the first function plus or minus the integral of the second function. Some simple integration rules for trig. I would take a moment to make sure that you get these down. These are things that you are definitely going to have to memorize for use later. The integral of cosine x dx is sine x plus c. The integral of sine x dx is negative cosine x plus c. The integral of secant squared x dx is tangent x plus c. The integral of secant x tangent x dx is secant x plus c. The integral of cosine x cotangent x dx is cosecant x. And the integral of cosecant squared x dx is negative cotangent x plus c. Particular solution. To find a particular solution, some additional information is required to find the unknown constant c. This information is known as an initial condition. As an example, find the general solution for capital F, and then find the particular solution given that capital F of 2 is equal to 8. We have a function that is defined as an integral. And so we're going to evaluate that integral to get the general solution, and then we'll use this additional piece of information to get the particular solution. So the first thing that I'm going to do is I'm going to separate this. The sum and difference rules. And so this will be rewritten as the integral of 13 dx minus the integral of x dx. And here I will use the constant and simple power rules. So the integral of 13 is going to be 13x plus c minus, now this is to the first power, so when I do that integral, it'll be x to the 1 plus 1 over 1 plus 1 plus some constant c. So here I'm going to simplify and reorder. The reason I'm going to do that is because I have, it's going to be x to the 1 plus 1, that's going to be 2, and then I'll have 2 in the bottom, so it'll be a half, so that'll be the highest degree value. So we'll have, let's see here, it'll be negative 1/2 x squared, and then it'll be plus this 13x, and here's the thing, I have a c here and I have a c here. They're not the same constant, and I don't know what they are, so I'm just going to put them together and call it a new c. None of those c's are the same. I don't know what they are. It doesn't matter. We can't know. And so we're going to put our box around this and call this our general solution. And then we're going to use this piece of information right here, this capital F of 2 equal to 8, to find our particular solution. So we know that if we plug in 2, so if I go 1/2 times 2 squared plus 13 times 2 plus c, I have to get 8 out of that. All right, so we can evaluate this. So 2 squared is 4 times negative 1/2 is negative 2 plus 13 times 2 is 26 plus c equal to 8. Negative 2 plus 26 is 24, and then I would subtract to get c by itself. So 8 minus 24 is going to be negative 16. And we get c equal to negative 16. And so if I go capital F of x is equal to, I have my negative 1/2 x squared plus the 13x, and then it'll be minus the 16. That is the value for c in this particular case. And so this is my particular solution. And we'll put a box around that, and we'll move on. Example, use the given indefinite integral and rewrite the expression so that it is in a form usable by simple anti-differentiation rules. Integrate the result and simplify the integral for your final answer. Now, one thing you're going to hear me say over and over again, there are no product or quotient rules for integration. And so when you come to a product or you come to a quotient, you are going to have to do something to fix that before you do the integral. You're going to have to rewrite it in a simpler way so that you can use the rules for integration. With this particular expression here, because there are no variables in the numerator, I can rewrite this thing as I'll bring the 1/4 out in front. I'll have my integral, and I will rewrite this exponent on the bottom as a negative exponent. And now, because I have rewritten it in this form, I can use the simple power rule on this integral, and I'll go 1/4 times x to the -2 plus 1 over -2 plus 1. And since it is an indefinite integral, I'll add my c. And so -2 plus 1 is -1. -1 on the bottom times the 4 will give me negative. So I'll have -1/4. And then this -2 plus 1 will give me a -1. 1 over x plus that constant c. And so my final answer will be -1 over 4x plus some constant c. And we will leave it like that. Next, find the indefinite integral of this given function here. So it is in the numerator x squared plus 2x minus 3 all over x to the 4th. Now again, we have a quotient. And again, note there is no quotient rule for integrals. So we have to rewrite this. So what am I going to do? I'm going to separate it into 3 fractions and simplify. So this will be the integral of, we'll have x squared over x to the 4th plus 2x over x to the 4th minus 3 over x to the 4th dx. So now what I'm going to do is I'm going to simplify each of these expressions and write them as separate integrals. And so we recall, if you have x squared over x to the 4th, we will subtract those exponents, and that will give me the integral of x to the -2 dx. I'll bring the constant 2 out front, and x to the 1st over x to the 4th. 1 minus 4 will give me -3, so I'll have x to the -3rd dx. I'll bring the 3 out in front, and I'll make that x to the 4th a negative exponent and put my dx, and I will use the simple power rule on each integral. So to integrate this first expression, I'll have x to the -2 plus 1 over -2 plus 1 plus 2 times the integral of x to the -3 plus 1 over -3 plus 1 minus 3 times x to the -4 plus 1 over -4 plus 1. And again, they were 3 separate integrals, so they would all need their own separate constant, but we don't know what any of those constants are, so I'm just going to put them all together right there. So here I'm going to simplify. And so we remember, put in our equal symbols here. Here we remember x to the negative 2 plus 1 will be negative 1, so I'll push it to the bottom and make it x with a 1 on top. Negative 2 plus 1 is negative 1, so I'll make that negative to keep it correct. Here I will have x to the negative 3 plus 1, which will give me negative 2. So I'll have x to the 2 in the bottom. Negative 3 plus 1 will be negative 2. Times 2 will just be negative 1, so I'll make a minus there with a 1 on top. Finally, I'll have x to the negative 4 plus 1 is going to be x to the negative 3, so I'll have x to the positive 3 on the bottom. Negative 4 plus 1 is negative 3. I have a negative 3 divided by a negative 3. That'll be positive 1, so this will become a positive. And then I'll have my plus c on the end, and we will put an equal sign, and we will put a box around that whole thing and call that finished. All right, last example. Find the indefinite integral of secant y times the quantity tangent y secant y. Okay, so here I'm going to say first we're going to distribute, and we will write this as the integral of secant y tangent y minus secant squared y, and this will be all dy. And now I am going to separate into two integrals. All right, so we're using the sum and difference rules here. So here we'll have the integral of secant y tangent y dy minus the integral of secant squared y dy. And now we're going to use the trig integral rules. And luckily for us, if we go back up to here, the integral of secant x tangent x dx is just secant x plus some constant c. All right, awesome. So this one is just secant y. And then the integral of secant squared x is just tangent x. So we have minus tangent y. And we should have had a constant for both integrals. So we're just going to put them both together and column C there. We'll put our equal signs in, put a box around this, and we will say that that is finished. Well, that's all I got for today, folks. So, the Star Wars fun fact of the day. Dennis Muren is a special effects giant. He helped George Lucas create ILM. He has been nominated for 32 Academy Awards in visual effects, and he has won 29. He is also the master behind other movies such as Jurassic Park, Terminator 2, and E.T. Well, that's all I got for today, folks. Have a great day. Bye.